Welcome back to AI Paper Podcasts. This is the series where we, really get into the weeds of the latest AI and tech research papers.
That's right.
Especially for you AI researchers, ML engineers listening in.
Yeah.
You're trying to stay ahead, and, well, that's what we're here to help with.
Absolutely.
So today we're looking at a really interesting one. It's called SimpleRL-Zoo, Investigating and Taming Zero Reinforcement Learning for Open Base Models in the Wild.
Yeah, quite a title. It's from Weihao Zhang and colleagues. HKUst, TikTok, and BUPT are involved.
Okay, so let's kick things off with a quick summary, maybe for the short form clips. What are the absolute key takeaways here?
Well, the big thing is this idea of zero reinforcement learning, or zero RL. Basically, training models using RL right from the start, the base model, with simple, rule-based rewards.
And the cool part?
The cool part is that this can apparently lead to emergent reasoning, like chain of thought, even self-reflection. They call it the aha moment.
Right, the aha moment. Love that. So previous work mainly looked at Qwen 2.5 models.
Yeah, and the issue there, or rather the observation, is that those models already seem pretty good at following instructions. So maybe not the best test case for emergence.
Gotcha. So this paper casts a wider net.
Exactly. 10 diverse base models, Llama 3, Mistral, DeepSeek Math, the Quinn series. And they found some pretty intriguing things, like longer answers don't always mean better thinking. They actually saw those aha moments, that verification behavior plop up in smaller models, non-Qwen ones, for the first time.
Okay, that's significant.
Definitely. Also, rigid reward formats.
Yeah.
They can actually hurt exploration, and the difficulty of the training data really matters.
Makes sense.
And maybe the biggest claim, zero RL genuinely improves accuracy, like pass-at-K accuracy, suggesting real learning, not just, picking the best guess out of a few tries.
So it's not just re-ranking.
They argue strongly against that. Oh, and one more thing, doing traditional supervised fine-tuning before RL might actually limit this kind of exploration.
Interesting. And they're open sourcing stuff.
Yep. Code, models, analysis tools, the whole package. So that's the 1-minute version.
Perfect. Okay, let's dive a bit deeper then. You mentioned zero RL. Can you unpack that a bit more, especially how it contrasts with the usual way of doing things?
Sure. So typically, if you want to use RL to teach a model reasoning, you first fine-tune it on a bunch of examples where humans have shown the steps that supervised fine-tuning, SFT.
Right, you give it the answers first, basically.
Kinda, yeah. You show it how to answer. Zero RL skips that. It jumps straight to RL, learning from trial and error with rewards, starting from the raw pre-trained model.
And the excitement came from DeepSeek R1.
Exactly. They showed you could get this emergent chain of thought stuff, even self-reflection, just from RL on the base model.
But that was a monster model, wasn't it? DeepSeek V3, like 671 billion parameters.
Huge, which naturally made people wonder, can this actually work for the smaller open models that more people can realistically use?
Right. And that led to the focus on Qwen 2.5, which you mentioned might be, well, maybe not representative.
That's the point this paper makes. The Quinn models, they already have pretty solid instruction following, maybe even some reflective abilities built in. So if zero RL works on them, is it the RL doing the heavy lifting, or is it just unlocking pre-existing potential?
It's like testing fertilizer on a plant that's already thriving.
Good analogy. You don't know if the fertilizer works on less fertile ground.
So this paper wanted to test that less fertile ground.
Precisely. They took 10 different base models, a real mix, Llama 3.18b, DeepSeek Math 7b, Mistral v0.17b, that's the older one, Mistral Small 24b, and then the Qwen 2.5 family from 0.5b up to 32b, hence the SimpleRL-Zoo name.
A zoo of models. Okay. And they applied the same SimpleRL recipe to all of them?
Pretty much. They used an algorithm called GRPO group ratio policy optimization following the DeepSeek recipe, and crucially, no SFT first, just base model plus RL.
What about the training data and the reward?
They used math problems, GSM-8K, and math data sets, and they found data difficulty was critical. So they made 3 sets, easy, medium, hard, each with about 8,000 problems. And the reward was super simple, +1 if the final answer was right, I know if it was wrong. That's it.
No penalties for weird formatting or anything?
Deliberately not. That's a key point they make later. Unlike some other studies, they avoided strict format rewards because they worried it would stifle exploration, especially for models that aren't great at following formatting rules initially.
That makes a lot of sense, actually. Let the model figure out the reasoning first.
Exactly. They also noted using simpler prompts for the models known to be weaker at instruction following, like the early Mistral and smaller Qwen models.
Okay, so diverse models, simple RL recipe, basic reward. Very data difficulty. How did they measure success beyond just, well, getting the right answer?
Right, that was another limitation they saw in prior work, just looking at accuracy and maybe response length.
Which you said can be misleading.
Totally. A model could just start repeating itself, making the response longer without getting smarter. So they looked deeper. They used a framework to analyze the type of reasoning happening. Borrowing from another paper, they used GPT-4o to classify parts of the model's output into behaviors like backtracking, verification, sub-goal setting, enumeration.
So looking for how it's thinking, not just the final output.
Exactly. Much richer than just counting keywords. They also measured the clip ratio, how often the model's output got cut off because it just kept going or got repetitive.
Ah, a sign of unhealthy length increase.
Precisely. And related to that, they looked at average stopped length, the average length of responses that did stop normally. Gives a cleaner signal than overall average length.
Okay, and pass at K.
Yep, pass at K accuracy. So what percentage of questions have at least one correct answer if you let the model try K times? This measures its ability to explore different solution paths.
Got it. So a much more nuanced evaluation setup. What were the main results then? Did it actually work across this diverse zoo?
It really did seem to. They showed significant accuracy gains across various benchmarks, GSM-8K, math, even tougher ones like Olympiad Bench and AIM for pretty much all the models. And this was with only 8,000 training samples.
Wow, only 8K samples. That's not a huge amount.
No, it's quite efficient. DeepSeek Math 7b, for instance, apparently tripled its performance on some metrics. And they saw response lengths generally increase too, like sometimes dramatically after just 80 training iterations.
Okay, but you said length can be tricky. What about the pass at K results? Did that support the idea of real learning?
That's one of their strongest points. They showed, using Mistral7b0.1 as an example, that pass at 8 accuracy grew robustly, eventually surpassing the initial pass at 1.
Meaning it got better at finding the right answer given more tries.
Right. And importantly, the gap between pass at 1 and pass at 8 widened during training. Even at pass at 128, there was still a big gap.
Suggesting it's not just getting better at ranking answers it already knew.
Exactly. They argue this strongly refutes the idea that it's just a re-ranking effect. It suggests the RL is genuinely improving the model's underlying ability to find correct solutions. It's exploration and reasoning.
Okay, that's compelling. But back to the length issue, were there cases where length increased but things went wrong?
Definitely. They highlighted Mistral7b-0.1, the older one. Its response lengths shot up, but so did its clip ratio, meaning lots of truncated, probably repetitive outputs. And its average stop length fluctuated wildly.
So more words, but not necessarily more sense.
Pretty much. It underlines that you can't just look at length in isolation. You need these other metrics like clip ratio and the reasoning behaviors.
Right, let's talk about those reasoning behaviors, the aha moment stuff. What did they find there?
This is really fascinating. They tracked the ratio of those behaviors: verification, backtracking, sub-goal setting, enumeration over training time. And they saw distinct patterns across different models. So the smaller Qwen models, 0.5b and 1.5b, seem to prioritize learning sub-goal setting first, breaking problems down. They also showed some growth in verification and enumeration.
Makes sense for smaller models learning the basics.
Yeah. Then you have models like DeepSeek Math, Llama 3.1 8b, and Mistral7b0.1 These showed big jumps in enumeration, and especially verification.
The self-checking part, the aha moment.
Exactly. Mistral7b0.1 for example, went from almost zero verification and backtracking to around 50% for both. That strongly suggests emergent self-reflection and correction.
Wow, okay. That's concrete evidence.
It really is. They even have examples showing the model's reasoning before and after. Like after training, Mistral7b0.1 starts plugging its answer back into the problem to check it, or explicitly says, let's try another possibility when it hits a dead end. Classic verification and backtracking.
That's very cool. What about the bigger Qwen models?
The 7b and 32b models. They already started with pretty strong reasoning behaviors, and those didn't change much during RL. Their response length also didn't jump as dramatically.
Suggesting for them, the RL was maybe less about learning new reasoning skills and more about, what, just thinking longer.
That seems to be the interpretation. They already had the skills. The RL maybe just encouraged them to apply them more thoroughly by increasing the response lengths.
And the unstable one, Mistral7b0.1.
Consistently low levels of all these positive reasoning behaviors, which fits with the high clip ratio and fluctuating length. The training just wasn't stable for that particular base model with this setup.
Okay, so The emergence of these behaviors, especially verification, really does seem linked to genuine improvement, and it happens differently depending on the model's starting point.
Precisely. It's not a one-size-fits-all process.
So digging into why things worked well or poorly, they looked at reward design, right? The format thing.
Yes. They ran an experiment comparing their simple reward, +1 for correct answer, with a reward that also required the answer to be in a specific format, like the latex box command. For weaker models like Llama 3.18b, forcing the format was bad news. Response lengths went up, but performance didn't, and eventually the training kind of collapsed.
Because it was struggling just to meet the format rules.
Seems likely. It couldn't explore reasoning paths effectively because it kept getting penalized for formatting. Even for a stronger model like Qwen 2.57b, the strict format reward eventually hurt performance and reduced the length of its chain of thought reasoning later in training.
So the lesson is, be careful with rigid formats, especially early on. Focus on rewarding the core reasoning.
Right. Prioritize getting the right answer through exploration, allows some flexibility in how it's presented.
And the other key factor was data difficulty.
Yes. They tested Mistral7b, the unstable one, and Qwen 2.57b, a stable one, on easy, medium, and hard math data sets.
What happened?
For Mistral7b, harder data made things worse. Performance tanked, lengths increased without accuracy gains again, training collapsed. It just couldn't handle the difficulty.
Too much, too soon.
Exactly. But for Qwen 2.57b, which started stronger, the easier data actually led to slightly worse performance and shorter response lengths compared to the medium-hard data.
Because it wasn't challenging enough.
Plausibly, it didn't push the model to improve its already decent reasoning. So, the takeaway is clear. You really need to match the training data difficulty to the base model's abilities.
That Goldilocks zone again. Okay, this brings us to the last major point. Revisiting the role of SFT. The supervised fine-tuning that usually comes before RL.
Right, the standard practice. They wanted to question that.
How did they test it?
They took Mistral24b and did a bit of SFT first, using a high-quality dataset called Numina Short, correct chain of thought examples. They did this for just 100 steps, and also for 500 steps, creating 2 SFT checkpoints.
And then applied the Zero RL training to those checkpoints.
Exactly, and compared it to applying Zero RL directly to the original base Mistral24b model.
And the results were counterintuitive.
Quite. The SFT gave an initial performance boost, as you might expect. The model started off better after 100 or 500 steps of SFT. But those models ultimately plateaued lower. Their peak accuracy and maximum response length achieved through the subsequent RLA phase were less than the model that started RL directly from the base.
So the head start didn't lead to a better finish.
Worse than that, the more SFT they did, 500 steps versus 100, the more limited the final performance seemed to be.
Wow. And what about the reasoning behaviors? Did SFT affect the emergence of verification and backtracking?
It did, negatively. The models that started with SFT showed less development of enumeration, verification, and backtracking during the RL phase. And again, more SFT steps led to a bigger drop in these exploratory behaviors later in training.
So the SFT, while teaching it some structure, might actually be preventing it from learning these more advanced, self-driven reasoning skills during RL.
That's the hypothesis. It seems like the SFT might sort of constrain the model, making it less likely to explore freely and stumble upon these more complex reasoning patterns that RL can potentially reward and reinforce.
It overfits to the SFT style, maybe?
Could be. Or it just narrows the search space too much. The author suggests we might need new cold start strategies that find a better balance between the imitation learned via SFT and the exploration driven by RL. Maybe different SFT data like longer code examples or entirely new techniques.
Fascinating. So it really challenges the default SFT then RL pipeline, at least for the goal of maximizing these emergent reasoning abilities.
It definitely raises questions and points towards needing more flexibility right from the start.
Oh, okay, let's try to wrap this up. The big picture seems to be Zero RL is a viable, even powerful technique across a range of models, not just the biggest or most pre-capable ones.
Yes, it can genuinely improve accuracy and generate more complex responses.
And the evidence, especially the pass at K results and the analysis of reasoning behaviors like verification, suggests this is real learning, not just smoke and mirrors or re-ranking.
Right. It seems to enhance fundamental reasoning capacity.
But success isn't guaranteed. You need to be smart about it.
Definitely. Careful reward design, avoiding overly strict formats is key. Matching data difficulty to the model's starting point is crucial. Understanding the model's innate strengths matters.
And maybe, just maybe, skipping that initial SFT step could unlock more potential for developing advanced reasoning through RL's exploratory nature.
That's the provocative finding, yeah. It suggests SFT might sometimes hinder more than it helps in the long run for this specific goal.
So overall, this paper gives us a much clearer map for navigating Zero RL training.
It really does. Provides practical insights and identifies key levers to pull.
And brilliant news for everyone listening. The researchers are open sourcing their code, models, and the analysis tools they used.
Which is fantastic. It lets the community build on this directly, replicate it, try variations. That's how the field moves forward.
Absolutely. It'll be exciting to see what people do with it.
Agreed.
All right, so maybe a final thought to leave everyone with, something to chew on. Given everything we've discussed, the power of Zero RL, the potential downsides of SFT for exploration, the importance of data difficulty, how should this change how we think about designing pre-training or fine-tuning strategies going forward? If we really want to cultivate these deeper reasoning abilities, maybe we need fundamentally different approaches from the very beginning. What does that mean for building AI that's not just knowledgeable, but genuinely adaptable and, dare I say, reflective?
That's the big question, isn't it? How do we best set the stage for reinforcement learning to work its magic on reasoning? This paper gives us some crucial clues, but there's clearly a lot more to figure out.
Indeed. Plenty to think about. Well, that wraps up our look at SimpleRL-Zoo. Thanks for tuning into AI Paper Podcasts.
Yeah, thanks everyone.
We'll catch you on the next one with more from the cutting edge of AI research.